just say a word about our speaker. It's Andrew Briggs, who did a degree in physics in Oxford, then came here and did a PhD, and I knew him back in the 70s and he did a PhD here. He then did a degree in theology, and then he went back to Oxford, where he is at the moment, maybe via some other places en route, I'm not sure, where he's now Professor of Nanomaterials, and hence the title of today's lecture, which is Nanotechnology, which some people have called grey goo, some famous people. So I hope he's going to tell us about nanotechnology and how it might relate to Christian faith along the way. So, Andrew, over to you.
Well, thank you very, very much indeed, Bob, for the invitation. Now, I should just make clear to you all that there are 3 lectures taking place simultaneously in Cambridge at this moment. One of them is the Archbishop of Canterbury is speaking. The second one is that Lord Brewers, former Vice-Chancellor of Cambridge, is giving the Wreath Lecture. And the third one is just me. And I'm neither of the other two. So if actually you thought you were coming to the Wreath Lecture or the Archbishop of Canterbury, I should quite understand if you want to leave now. What is nanotechnology? Well, a report that was put together by a combination of the Royal Society and the Royal Academy of Engineering that came out last summer identified 2 topics. Nanoscience is the study of phenomena and manipulation of materials at atomic, molecular and macromolecular scales, where properties differ significantly from those at a larger scale. And then nanotechnologies are the design, characterization, production, and application of structures, devices, and systems by controlling shape and size at the nanometer scale. So I'll talk a little bit more in a moment about what a nanometer is, but loosely speaking, people think of nanotechnologies as being a sort of 100 nanometers or less. They think of nanoscience as being studying materials and systems and devices at that scale. And they think of nanotechnologies as actually manipulating them and doing engineering with them. And the key point is that nanotechnology becomes interesting when small is not the same as big. In other words, the very smallness of the materials and structures that you're looking at makes a significant difference to their properties and behavior. So it's helpful to think of these things on a series of different scales, and on this scale here, up here is a meter, and then every time we move a tick to the right, we divide by 10. So that's 10 centimeters. A football is somewhere around here. And then as we come down, that's 10 millimeters. That's 1 millimeter. There's a little tiny flea that you might just be able to see on your eye. I don't know who it came from. Human hair is there, about 80 thousandths of a millimeter. So this is a thousandth of a millimeter or micrometer there. Oh, sorry, that's a micrometer there. We're getting down to blood cells here, and then even smaller little viruses and so on, at a scale of about 1/10 of a micrometer. That's a 10,000th of a millimeter. And we can think of that as 100 nanometers, and that's beginning to be the onset of nanotechnology there. And then we go down smaller and smaller. And at the scale of 1 nanometer, which is 1,000th of 1,000th of 1,000th of a meter, if I'm getting it right, a billionth of a meter, we've got something the size of 60 carbon atoms, which, by a fascinating coincidence, are arranged geometrically in a pattern that maps onto the football over here. And then down here, you've got that scale drawn out on, in this case, a linear scale. And we'll look at 1 or 2 of these things as we go through. And DNA would be down here, sort of close to a nanometer in diameter. Now, another way of visualizing all that presents a considerable technological challenge, which I shall try to address. We'll come back to this picture in a moment. But we can sort of zoom out and imagine that we're looking here at the Earth. And there's the Earth. It's about, whatever it is, 10,000 kilometers in diameter. And as we zoom in, there's the planet Earth. We can imagine ourselves operating our zoom and looking at things in higher and higher magnification. Now we're about 500 kilometers across the picture. And there's a football pitch, and that's about 2 kilometers across. And now as you zoom in on that, we're zooming in until we've got down to something that's about 2 meters across. Well, that's what it says. So I suppose the man's about 2 meters high. And there's the football on his T-shirt, or he's kicking it. And as you zoom in, so you begin to see things in greater and greater magnification. And this particular footballer has got a flea in his hair. So there's his human hair. And remember, the human hair is 80 micrometers in diameter, 80 thousandths of a millimeter. And there's the flea clinging onto it. And there we are. We're about 15 millimeters across in that whole picture. Now the picture is about 1 millimeter across. And as we zoom in more, we begin to see some red blood cells. And the red blood cells are about 10 micrometers in diameter. And then as we zoom in a bit more, whoops, lost it. We begin to see things like DNA and nanoparticles. And now we're beginning to move into the realm of nanotechnology. So now we've had to move away from what you might actually see down a microscope to ball and stick models. Of course, the first one of DNA was famously made not very far from here. And now we're looking at something that's about 100 nanometers across in the picture. And now we begin to look at it more. And here is that buckyball, remember. It says 10 nanometers. Actually, this particular thing here is about 1 nanometer across, and it's got the same pattern on it as the football. And those we can actually see. We can see those buckyballs, and I'll show you some pictures later on. And now we're beginning to move into the realm where all you can do is start to draw cartoons. So here we are. We're about 1/10 of a nanometer in diameter, and we're moving to the stage where you could never see a picture like this with any microscope at all. You can just draw cartoons of them, and so on into the atom. So does that give you a picture of how one might zoom in across those different size scales to get some feeling for where the realm of nanotechnology lies? It's in this sort of regime of sort of 100 nanometers down to about 1 nanometer. Well, now, when one thinks about working in this realm of things that are below about 100 nanometers or so, there's an awful lot of people who realize that they've been working in this realm for years and years and years without ever calling it nanotechnology at all. For example, the great majority of chemistry is done on that scale. And so this reminds one of this scene in Molière's Le Bourgeois Gentilhomme, where the tutor is teaching Monsieur Jourdain about how speech works and so on. And he explains to Monsieur Jourdain what prose is. And Jourdain says, well, what do you know about that? These 40 years now I've been speaking in prose without knowing in it. How grateful I am to you for teaching me that. And I think there are an awful lot of people around who for at least 40 years have been working in nanotechnology without ever knowing it, and they're grateful now to be told about it. Our bodies have used nanotechnology all our lives. And there's some remarkable kinds of nanotechnology going on in the body. Your stomach works by marvelous little nanotechnology motors pumping stuff in and out from place to place inside your body. And in fact, just our muscles, anything that we move when we want locomotion. This is a little movie of the way that myosin works when your muscles contract and expand. Many of the mechanisms were discovered by Andrew Huxley, who I think was working in London, but at least living in Grantchester. And that's a kind of nanotechnology. And those things are found in the natural world, found in our bodies, and some people see amazing design in them, and I'll come back to that later. But of course, the nanotechnology primarily means what we can do and ways that we can engineer things, and that has gone from strength to strength in recent years. Here's an example of using a beam of gallium ions to cut away a groove in a high-temperature superconductor. And this is a scale of about 500 nanometers, and you can see that the ion beams are milling this material with terrific precision, and you can use those to do machining of materials on a scale down to about 50 nanometers. One of the breakthroughs in the field came in 1990 when Don Eigler, working at IBM laboratories in Almaden in California, moved individual xenon atoms around on a surface, and because he was working for IBM and he wanted to get a pay rise, he thought a good way to do it would be to write the IBM logo. And each of these is an individual xenon atom that he's moved to the place where he wanted it to be. And so that means you got to the stage 15 years ago when you could move atoms on a surface to a location of your choice. One of the great drivers for nanotechnology is the progress that's being made with computers. And here on this slide you have the illustration of, well, Babbage's original calculating machine that stood, I suppose, about a meter tall. And that has progressed to the transistors and now the integrated circuits that have been in use for 30 or 40 years in computers. And the question is, how much smaller can you go on making them? This is a little device that was made in Tsukuba in Japan. And this is a single electron transistor made with titanium dioxide on a titanium surface. And even this picture is about 10 years old now, so this has been around for some time. The head of Intel, a man called Gordon Moore, observed that computers were getting smaller and smaller and faster, and that the number of transistors on a chip was doubling roughly every 18 months. He noticed that some years ago. It's become known as Moore's Law, and it's amazing the extent to which that trend has been maintained. Moore's Law is a wonderful thing to show to management, because all you do is you put a linear scale of years along here and a logarithmic scale of almost anything you like to do with computing up there, and you'll probably get a straight line. And if it's something you want more and more of, it'll be a straight line going up, and it's something you want less and less of, like the number of electrons per device, you'll find it coming down. And this is the number of electrons per device on a logarithmic scale, going up to about 2006 or so. So this is a projection for next year. And the thing that this slide illustrates is that by about 2015 or so, you'll be getting down to 1 electron per device. So how do you get smaller than that? And so you're hitting the regime where the quantization of matter is beginning to make a difference. And that's either going to stop you making further progress, or it may turn out to be something that you can exploit. If you want an illustration of Moore's Law in practical terms, in 1974, just over 30 years ago, Cambridge had one mainframe computer. It was an IBM 360. and the random access memory of the computer was increased from 2 megabytes to 3 megabytes, and it was such a big event that it was the talk of the town. Everyone in Cambridge was discussing it. The other day, I bought a little bit of memory here on this chip. It's half a gigabyte, so it's about 500 megabytes, and it cost £20. And that's the practical illustration of the extent to which Moore's law is moving us along. Now, driven by these things and other considerations, people are studying the materials on this tiny scale. And let me give you an illustration of the kind of thing that we do in our own lab in Oxford. We look at these little buckyballs. Here's a cartoon of it, but here are some actual pictures of them. So this is a transmission electron micrograph. This is a single-walled carbon nanotube. It's got a diameter of about 1.4 nanometers, and each of these objects inside it is one of these little balls made up of 60 carbon atoms. When you buy your 2006 edition of the Guinness Book of World Records, you'll not only find an entry from Colin Humphrey's laboratory of the smallest hole which he drilled, but you'll also find an entry for the smallest test tube. And you'll see pictures like this. And the reason it's the smallest test tube is that we did some experiments where we had a little length of this, about 10 nanometers long, and we put 5 molecules inside of C60 atoms and 2 or 3 C60 molecules and 2 or 3 oxygen atoms, and we could actually watch the reaction taking place. And the volume of that test tube is 10 yoctoliters. And if you want to know what a yoctoliter is, it's 1,000th of a zeptoliter. So the volume is 0.01 zeptoliters. The number of yoctoliters in a teaspoonful is roughly equal to the number of teaspoonfuls in all the world's oceans. And if you actually were to look over the shoulder of Andrei Klobostov, who took the pictures, this is the sort of thing that you would see in the electron microscope. So here's our single-walled carbon nanotube. And then these molecules actually have 82 carbon atoms inside them. And then inside each one of these there is 1 atom of cerium. So you're seeing 1 atom of cerium inside a cage of 82 carbon atoms that's inside this single-walled nanotube. And that's about 1.4 nanometers diameter, something like that. Well, now, I hope that these pictures here give you a glimpse of what real nanotechnology really looks like. But as you well know, there's a great deal of confusion around about nanotechnology, sometimes propagated by people who ought to know better. And I'd like to tell you a little bit about where this confusion comes from and what the sources of confusion are. I think nanotechnology was first popularized by a film that was made in 1968. And it was a film made of Isaac Asimov's science fiction novel, and it was called Fantastic Voyage. And I'm told that at the time everyone went to see it because it starred Raquel Welch. And it's the story of some scientist who's crucial to the US defense effort, who gets some sort of problem of clotting or something in his brain. And the way they decide to solve this is to put the scientists and a crew and Raquel Welch inside a submarine and shrink it down into a size where it can travel along the blood vessels and get to the brain, and then they can do laser surgery up in the brain and fix everything. I did actually watch the film to find out what it was about. It's incredibly boring. I don't recommend it. They have to have a series of crises. So one of them is when they go through the heart, and there's great turbulence because of the heart. And of course, there's a great deal of science that wouldn't work, because if you shrunk a laser down to that size, the wavelengths would be all wrong and so on. Then there was a more recent film called Agent Cody Banks that was made in the year 2003, and I'll show you a clip from that in a moment. The person who I think has done more to inform and to misinform the public about nanotechnology is a man called Eric Drexler. He's a sort of, well, I think people can't decide whether he's a nutter or a harmless enthusiast who works out of Palo Alto in California. And he put out more than one book. This is Engines of Creation, in which he has all these fantastic machines that are supposed to be assembling things at a molecular level. This is a cartoon. This is a picture taken from his book, and these are supposed to be individual atoms. And you see, you have this marvelous desktop self-replicating machine. And the whole thesis of his early work was that you could create, at an atomic level, self-replicating machines. And most professionals in this field find it so fantastic as to be not worthy of serious credence. The most famous person who's written about it is Richard Smalley, who was one of the three people who was awarded a Nobel Prize for the discovery of fullerenes. And in Drexler's vision, the self-replicating machines are very, very much smaller than viruses, which are the smallest known self-replicating things in biology, and certainly a great deal smaller than cells. Well, now, when people talk about what's nanotechnology going to do for us, you get two extremes. You get one extreme, which is that nanotechnology will save the world. So let me show you this from Agent Cody Banks. Well, the concept of nanotechnology became encapsulated in this public phrase of grey goo. And here are three quotes about it. The first one's from Eric Drexler that I mentioned to you a moment ago. As engines of destruction, nanotechnology and AI, artificial intelligence systems, will lend themselves to more subtle uses than do nuclear weapons. A bomb can only be used to blast things, but nanomachines and artificial intelligence systems could be used to infiltrate seas or control a territory or a world. The American Spectator, the nightmare is that combined with genetic materials and thereby self-replicating, these nanobots would be able to multiply themselves into a grey goo that could outperform photosynthesis and usurp the entire biosphere, including all edible plants and animals. That was 2001. But The Guardian commented later that year, grey goo is a wonderful and totally imaginary feature of some dystopian science fiction future in which nanotechnology runs riot and microscopic earth-munching machines escape from a laboratory to eat the world out from under our feet. Well, the Agent Cody Banks film goes on like this. Well, there you are. There was a book by Michael Crichton called Prey, in which the hero, Jack, discovered his wife's firm had created a self-replicating nanotechnology, a swarm of microscopic machines. And originally meant to serve as a military eye in the sky, the swarm escaped into the environment and is now seemingly intent on killing the scientists trapped in the facility. And the dust jacket says, drawing on up to the minute scientific fact. Prey takes us into the emerging realms of nanotechnology and artificial distributed intelligence in a story of breathtaking suspense, which was read by His Royal Highness Prince Charles. And in 2003, the headlines read, Prince Charles fears grey goo nightmare. Grey goo that phrase doesn't actually appear anywhere in Michael Crichton's book. And a year later, Prince Charles had to say that he was misrepresented and that he did not believe in self-replicating nanotechnology. Well, now, what are we to make of all this, and what are we to make of it in particular from the Christian perspective? And I really want to take those two areas of nanoscience and of nanotechnology and look at them one at a time. And the first one is the question of nanoscience. And as we see these quite remarkable examples of nanotechnology, either in biological systems or that we can create and study in the laboratory, does that make a difference to our understanding of God as creator? And to shed a bit of light on this, I want to draw out four belief paradigms. And the first one is the position of the agnostic, which was coined originally by T.H. Huxley in the 19th century to mean one who holds that the existence of anything beyond material phenomena cannot be known. But although he coined it in that very precise sense, he rather quickly lost control of the term, and it came to mean a sort of, excuse for sitting on the fence and not making up your mind. Apparently, someone went to Benjamin Jowett, the master of Balliol in the last century, and proudly told him that he was an agnostic. And Jowett replied, "Young man, in this university we speak Latin, not Greek, and the Latin for agnostic is ignoramus." Atheism means a disbelief in or a denial of the existence of God. The first use of it in the Oxford English Dictionary is from Francis Bacon in the 17th century. A little superficial knowledge of philosophy may incline the mind of man to atheism. Deism is a technical term which was apparently first used by Richard Bentley to mean belief in the existence of God with a rejection of revelation. It's closely allied to the concept of natural religion. And then finally, theism, which the OED defines as belief in a deity or deities as opposed to atheism. And specifically, belief in one God as creator and supreme ruler of the universe, and specifically, it's in distinction to deism. In other words, it does not deny the revelation. So you can sort of summarize that in tabular form like this, that if you have two columns, one of them is creator and the other one is sustainer, agnosticism claims that you cannot know. Atheism denies that there's a God at all, so he's neither creator nor sustainer. Deism acknowledges that there's a God who creates everything, but denies that there was any subsequent revelation and denies God's activity in the world now. And theism affirms God's activity in creation and his activity in the world now. Indeed, there's really no distinction between the two. It's a false distinction to make. Now, the significance of that comes when you try to examine the argument from design. And the old argument from design says, well, the exquisite structure of the world and of animal systems, and we might now say of biomolecular systems, seems to be perfectly intended for their optimum function. What's the origin of this? Paley, early in the 19th century, used the analogy that, if you find a watch on a beach, there must be a watchmaker. And I think Charles Darwin said that Paley's work was one of the few things he really benefited from when he was studying here at Cambridge. The argument from design has re-emerged recently in the particular form of so-called intelligent design. There was a tour last year by a man called Philip Johnson, who is a professor at University of California at Berkeley, and is a lawyer, actually. And he was touring the UK, advocating something rather analogous to intelligent design. But many people have come across intelligent design through a book called Darwin's Black Box, written by Michael Behe, who I think is a professional biologist by training. And loosely speaking, you can say that intelligent design admits that evolution occurs, but identifies lacunae in the evidence for evolution, where it says, you see there, that must have been God working. That shows that there's an intelligent designer behind it all. And an important component of this kind of argument is that you have to show the inadequacy of the normal scientific study in the field. So in Behe's book, fairly early on in chapter 1, he writes, "This book is about an idea, Darwinian evolution, that is being pushed to its limits by discovery in biochemistry." Then he says, "When sciences such as physics finally uncovered their foundations, old ways of understanding the world had to be tossed out, extensively revised, or restricted to a limited part of nature. Will this happen," he asks, "to evolution by natural selection?" I'm not sure that many physicists would recognize that old ways of understanding were tossed out by new discoveries. And I'm not sure how many biologists would subscribe to that. But whatever the details, the fundamental understanding is coming from a mistaken kind of view about how God works in the world. So here's a little picture of a green circle which encapsulates all observed phenomena. And if you have no science at all, then none of it can be explained, and so all of it is caused by God. Well, now, as science progresses, so you begin to get bits on the left-hand side that we can explain, and those are caused by science, and so there's a little bit less that's caused by God. And now, as science progresses, I suppose we could extrapolate to the time when we'll be able to explain the whole lot. Carl Sagan, in his foreword to A Brief History of Time by Stephen Hawking, talks about a universe with no edge in space, no beginning or end in time, and nothing for the Creator to do. This picture is sometimes known as, described as God of the Gaps. And just before Professor White wishes he'd never invited me to speak, I should quickly show you that that picture is completely and absolutely wrong. It's wrong for all sorts of reasons. It's wrong to think that all observed phenomena is a sort of constant thing. Actually, I think the observed phenomena are expanding rather faster than our ability to explain them. But it's most wrong by supposing that what we can give an account of scientifically is therefore no longer caused by God. Rather preferable, I think, is the inscription that you'll find if you walk down Free School Lane on the doors of the old Cavendish Laboratory, where now I suppose the materials department is, and we've got at least 2 professors of materials here and various other distinguished research fellows as well. So if you go in from the Free School Lane entry, you'll pass that inscription. It's in Gothic script, so it's not very easy to read, and it's in Latin, which a decreasing proportion of Cambridge scientists are able to translate. There's a rather interesting story of the sequel to that, which is described in the European Journal of Physics in an article on the Cavendish Laboratory by Professor Sir Brian Pippard. And he said this: the great oak doors opening on the side of the original building had carved on them by Maxwell's wish the text from Psalm 111, Magna opera Domini exquisita in there's a misprint there, in omnes colorantes eius. Shortly after the move to the new buildings in 1973, he describes, a devout research student suggested to me that the same text should be displayed in English at the entrance. I undertook to put the proposal to the policy committee, confident that they would veto it. To my surprise, however, they heartily agreed both to the idea and to the choice of Coverdale's translation, inscribed in mahogany by, it was later inscribed in mahogany by Will Carter. He also talks about the legend that when Rayleigh wished to use the same text, that's Lord Rayleigh, wished to use the same text to stand at the beginning of his collected papers, CUP demurred on the grounds that some might misunderstand who was the Lord referred to. But the text does actually stand in his collected papers. Anyway, I was that devout research student referred to there, and here is the entrance to the new Cavendish Laboratory with the text carved in the William Coverdale translation. So I love that, because what it says is that what scientists in the Cavendish Laboratory, and in any other laboratory for that matter, are doing is studying how God makes the world work. And you could not get further away from the God of the gaps than that. Now, let me go on rather more briefly to this question of what should we be doing with our new capabilities in nanotechnology? How should we be using it? And particularly, how should we answer the challenge that we're not supposed to play at God? A key text in this is in Genesis, where the writer describes God making man in his own image. And the word for image is this root here, SLM, here. And it's a very rich word with a wealth of meaning in it. And the meaning can relate both upwards to man's relationship to God, and outwards, or downwards if you like, to his relationship to that over which he has dominion. So I think that everybody would agree that the word image there refers to the whole of man, not just his intellectual bit. In its original Hebrew, it means predominantly just another one, a duplicate. It refers upwards to a relationship with God. In other words, it means having similar properties to, and therefore the capacity to relate to. Klaus Westermann in Creation said, mankind is created to stand before God. And Eichrodt, in his theology of the Old Testament, said, personhood is bestowed on him as the distinctive characteristic of his nature. So those are their expositions of the image of God. But it also refers downwards to man's relationship to creation. Man is God's executive to take responsibility for the world, is von Raad's account. Man himself is the image of God who has no image of his own. And he's referring there to the fact that if someone conquered a territory in the ancient Near East, they would set up a statue of themselves to remind people who was boss. And it therefore includes the concept of accountability. Charlie Mole put it like this: perhaps the most satisfying of the interpretations of the meaning of the image of God in man is that which sees it as basically responsibility. I want to end with talking about something that is being opened up by nanotechnology, particularly in the implementations of information processing. And this relates to new insights that have come about in the last 20 years or so about the physical nature of information. Now, I say in the last 20 years or so because that's how the timescale over which people have begun to realize their significance in the scientific world. But of course, you could go much further back to John's Gospel, where John talks about the Word becoming flesh, kai ho logos sarx egeneto. And I've given you a word-for-word translation of the Greek there, because it emphasizes how there's a juxtaposition in the sentence of word and flesh. And logos was a very rich term at the time that John was using it. It had a Hebrew origin, meaning the word of God as something active that came from God and did things. And it had a Greek connotation, particularly from the writings of Philo, as a sort of encapsulation of, I don't know, some sort of controlling principle of the universe. And John is describing how in Christ this logos, with all this rich connotation of meaning, actually became physical. And people have been beginning to realize how a lot of the things that we would hitherto have thought of as abstract quantities have a physical embodiment that is inseparable from their very nature. I think that biologists and psychologists have been realizing this for some time. I've put there one or two quotes from the world of psychology, most of which I got from Malcolm Jeeves, showing how, or illustrating how concepts like behavior and personality and one might almost say responsibility and belief are inseparably embodied in the physical stuff of the brain. And there's been a growing evidence for that, I suppose most recently and most notably from functional magnetic resonance imaging. In my own field, people have been realizing more and more through the 20th century that information that one might previously have thought of as a sort of abstract quantity is in fact physical. In the 1940s, Shannon did some very important work developing the mathematical nature of information. And it turned out that the mathematics that was used to describe information in a noisy environment was exactly and precisely the same as the mathematics that had been developed for statistical physics in the 19th century to describe gases and so on. And that's why in information theory, terms like entropy have come to be used. And all of the communication that we do, every time we make a phone call or use the internet or anything, we're using technology that's been stored by engineers that have grown up trained in Shannon's mathematical theories of information. In 1985, a marvelous eccentric who lives up on Headington Hill in Oxford called David Deutsch, who over the years has got more and more out of phase with the sun, actually. He now gets up about sort of tea time in the afternoon, started to talk about the physical nature of information. And the insights that he got from that were that once you realized that information was physical, and you saw that at the tiniest level, at the most what we would now call nanotechnology level, things are obeying the laws of quantum physics, then information must be capable of being described in quantum form, and that would open up whole new possibilities for what you could do with information processing. And this paper of his in 1985, many people regard now as the manifesto of quantum computing. And of course it's led to an absolute explosion of research in the field. A great skeptic of quantum computing in the early days was a man called Rolf Landauer. He, before he died, became a little bit less skeptical, and he actually wrote a paper whose title has become something of a catchphrase. The title of the paper was The Physical Nature of Information. Much of the paper is about quantum computing. But he also went on to talk about what this taught us about the nature of the world, and in particular the relationship between theory and experiment. And actually he ended up with a rather sort of anti-Platonic kind of approach, saying, well, it's not really that in the beginning was theory and then, the physical world is the outworking of that. He would rather put it the other way around, or at least have a hermeneutical circle. But it's rather interesting that in describing this, he ends up quoting from the beginning of John's Gospel, which I think brings us back to the point that in Christ, John is describing how something that was not physical became physical and encapsulated in a human form. Well, I've taken you on a little bit of a tour, and it's time to stop, but I hope I've given some idea of what nanotechnology is, some idea of the real things that we can do with nanotechnology, and both in the biological world, the medical world, and in the computing world, and actually, one would have to say, in a number of other worlds. There are some very exciting things that can be done. In the popular mind, there is probably more disinformation about nanotechnology than accurate information, and I hope that those of us who are scientists can help to put that right. And the developments in nanoscience and in nanotechnology will raise in new forms the questions about what do we learn about the Creator from our study of science, and what sort of responsibility are we called upon to exercise as these new capabilities become available to us. So let me end with a sort of thing to think about and you to dream about in your sleep. Here's a little picture, and the finishing question is, as you look at that picture, which I suppose is supposed to be a set of red blood cells with this little nanobot injecting them, where does that lie on the spectrum between technological feasibility and pure fantasy?
Thank you very much.